Okay, section 11.3. We are solving equations with quadratic methods. So we have two things to do in this section. The first is to solve equations that we call, or that we say are quadratic in nature. Quadratic in nature / form. So they aren't quadratic, but they behave quadratically. And the second thing we're going to do is problem solving, which we know means word problems. Wow, what happened to my S there? Solve it. Okay, so we spent the last two sections looking at completing the square, quadratic formula, and we have some basic steps for solving quadratic equations. Number one, if we have something like ax plus b quantity squared equals c, we just use square roots to solve this. I'm going to take the square root of both sides, make sure that we have our plus or minus square root of c, and then solve for x. We get two answers. If we don't have this form, then we make sure that we write the equation in standard form. Remember, standard form is ax squared plus bx plus c equals 0. And then we should always start by trying to factor. Try to factor, and if we can't factor, we complete the square. Or we use the quadratic formula. That's kind of our basic formula for solving quadratic equations. Now, what this section is all about is what happens if we don't have this nice form, we don't have a standard form because it's not quadratic, but it does kind of look like it would work the way that a quadratic equation would. So let me show you an example. Let's say we were told to solve x minus the square root of x minus 6 equals 0. So this is what we call quadratic in nature or quadratic in form. I'll write that out. This is quadratic in nature or form. And the reason for that is if we let u equal the square root of x, then u squared is the square root of x squared, or just x. And if we make these substitutions, our old equation becomes u squared minus u minus 6 equals 0. And so this is quadratic in u, but u is not quadratic. The original equation is not a quadratic equation. There's no x squared anywhere. But it does behave as a quadratic function, u squared minus u minus 6. So from here we can solve. So now we have it in standard form. We look to factor, or we complete the square and use quadratic formula. So this one happens to factor to u minus 3 times u plus 2 equals 0. And we know that's going to give us u equals 3 or u equals negative 2. Now, this is where we have to add some extra bits when we have these quadratic in nature equations. Because they're not true quadratics, we're solving them quadratically, we have to go back and check our work. So we actually did this back in chapter 7 when we were doing rational functions and rational equations. Every time we get a quadratic equation and we'd use the quadratic formula, back then we said we have to go back and check to make sure we don't bump out of the domain. Now those are actually quadratic equations in form or in nature, just like these are. So the same thing applies here. We have to, double star. We must check our work. So check the solutions in the original. Well, if we're going to check on the original, that means we need to get x values, which is what we wanted anyway, because the equation didn't ask for u's, it asked for solutions with x's. So that means the square root of x, because that's what u is 3, or the square root of x is negative 2. And so that means that we have x equals 9 or x equals 4. So now we can go back and check these. So we have 9 minus the square root of 9 minus 6 should equal 0. And 4 minus the square root of 4 minus 6 should equal 0. This is 9 minus 3 minus 6 should equal 0. That one works. This is 4 minus 2 minus 6 should equal 0. This one does not work. So we take this, we cross it out, and x equals 9 is our final answer here. And this comes down to the square root principle. Inside of our equation, the square root of 4, even though it's got a minus here, the minus sticks around, so this is just the principal root or the positive root, which is why this is the 2. Every time you solve a quadratic equation that's only quadratic in nature or in form, sometimes all of your solutions will work, but a lot of times you're going to have these extraneous solutions, these things that aren't actually solutions. They solve the quadratic version, but they don't solve the actual equation. And that's because we're solving non-quadratic equations quadratically. So every time you do that, you open yourself up to having solutions that don't actually work. So let's try another one here. So we are going to solve p to the 4th minus 3p squared minus 4 equals 0. Again, this is quadratic in nature, and you're always looking at this term to see if you have a quadratic in nature. So just pick whatever letter you want. I'm going to choose x because they're p's. So if x is p squared, then x squared would be p to the 4th. And substituting that in, we would have x squared minus 3x minus 4 equals 0. Excuse me. So if you're ever not sure, just take this term, ignore the coefficient, so just the variable term, let that equal some other letter, and then square it. When you substitute in, if you get a nice quadratic equation, you know that it was quadratic in form. If you don't, then you don't have a quadratic in form, and you can't be solved using quadratic methods. So now we're going to solve this. Again, we look to factor. This one does factor to x minus 4 times x plus 1. So that means x equals 4 or x equals negative 1. We have to check in the original. So that means that p squared equals 4 or p squared equals negative 1. Now this, p squared can never equal negative 1. Or in this case, it can equal negative 1, but now since we allow for complex solutions, p would just equal I. And over here, p would equal plus or minus 2. And this would actually be u squared, this should be plus or minus I. So we have 4 solutions, and just to make this clear, we're doing p equals the square root of negative 1, so p equals plus or minus I. Because our square root principle still holds, when we take the square root, we still need our 2 answers. So when we go back, we have 4 things to check. So we're going to do 2 to the 4th minus 3 times 2 squared minus 4. This should equal 0. 2 to the 4th is 16. Minus 12 minus 4. That definitely equals 0. And now we need negative 2 to the 4th minus 3 times negative 2 squared minus 4 should equal 0. Now since we're raising negative 2 to even powers, this is going to work just like the positive 2 case did. Negative 2 to the 4th is positive 16. Negative 2 squared is positive 4, so that's negative 12 minus 4. Still going to equal 0. Now we're going to plug in our i's. So we have positive I to the 4th minus 3 times I squared minus 4. I to the 4th is 1. I squared is negative 1, so this becomes plus 3 minus 4. That does equal 0. And we plug in negative I to the 4th minus 3 times negative I squared minus 4 should equal 0. Negative I to the 4th is just negative 1 to the 4th times I to the 4th, so this is still positive 1. Negative I squared is just negative 1 squared times I squared, so this is still negative 1 times negative 3 makes this positive 3. Minus 4 equals 0. That one works. So our solutions, plus or minus 2, plus or minus I. So this is an example of a quartic equation. Now quartics you can think of as just souped up quadratics, p squared and p versus p to the 4th and p squared. And so even though these aren't quadratic, all 4 of our solutions still work because quartic equations, by and large, operate a lot like quadratic equations. So let's look at 2 more examples before we jump into a word problem. So all these examples that we're doing are the classical quadratic in form type of equations that we want to be on the lookout for. Some of them are easier to spot than others. The last one we just did with the p to the 4th and p squared, most people are able to see that after a couple tries that, oh yeah, that's going to be a quadratic type equation. So this one we have x minus 3 squared minus 3 times x minus 3 minus 4 equals 0. This is the other one that most people are able to identify is quadratic because it's, still quadratic. It's got a square, it's got a single power. But inside that square, we're going to set this equal to y is x minus 3. So that we get y squared minus 3y minus 4 equals 0. This is going to factor to y minus 4, y plus 1 equals 0. And that means y equals 4 or y equals negative 1. Now we'll come back to the x's, and we have x minus 3 equals 4, so x equals 7. And we have x minus 3 equals negative 1, so x equals 2. And the nice thing is that this was quadratic, so both of these solutions should work. Now, because we made this substitution, we should check just to be sure. So 7 minus 3 squared minus 3 times 7 minus 3 minus 4 should equal 0. So it's 4 squared minus 3 times 4 minus 4 should equal 0. 16 minus 12 minus 4, still 0. And then over here, 2 minus 3 squared minus 3 times 2 minus 3 minus 4 should equal 0. 2 minus 3 is negative 1 squared. Minus 3 times negative 1 minus 4 should equal 0. Negative 1 squared is just 1. This is plus 3. And that definitely still equals 0. So both of these are solutions. So we always want to check, only because we're doing the substitution here. Excuse me. All right, so our last problem before we jump into some word problem, we're going to solve x to the 2/3 minus 5x to the 1/3 plus 4 equals 0. So again, this is a pretty classic quadratic inform type problem. We're always going to key in on this term. So we'll set y equal to x to the 1/3. That makes y squared equal to x to the 1/3 squared, or x to the 2/3. So swapping out x's for y's in the original, we have y squared minus 5y plus 4 equals 0. So this one is quadratic. It looks like a nice quadratic. So we solve this. Look to factor. This one also factors to y minus 4 times y minus 1 equals 0. So y equals 4, or y equals 1. Excuse me. So now we need to go back to the x's. So that means x to the 1/3 equals 4. And we cube both sides. So that means x equals 4 cubed, or 64. And we have x to the 1/3 equals 1. Again, we cube both sides, so x equals 1. Now this thing is definitely not quadratic, so we absolutely need to go back and check. So let's start with the 64. So plugging 64, we have 64 to the 2/3 minus 5 times 64 to the 1/3 plus 4 should equal 0. Space here. Let's jump up to the next page. So 64, remember we do this in the order that's easiest. The 1/3 power of 64 we know is 4, so this is 4 squared minus 5 times 4 plus 4. So this is 16 minus 20 plus 4. And this is 20 minus 20, still 0. And then over here, we can do the 1. So this is 1 to the 2/3 minus 5 times 1 to the 1/3 plus 4 should equal 0. Well, 1 to any power is still 1. Minus 5, 1 to any power is 1. Plus 4, and that one definitely equals 0. So we have x equals 1, 64 are our solutions. Checked and worked. So we've seen 4 examples now. All of these are, as I said, the classic examples of quadratic in nature equations, so things that act quadratically that don't look like a quadratic, except of course this one. This one is a quadratic. It's just making a little substitution. So in the homework you'll have more practice Seeing more of those, getting used to making your substitutions. Remember, you're always keying in on this term. So always be looking at where the quote-unquote linear term should be. And then just square that and see if you, when you substitute, you get a nice quadratic. Excuse me. All right, so let's take a look at a word problem that requires us to use quadratic methods. So beach and Fargo are cities that are about 400 miles apart. Miles apart. A salesperson leaves Fargo heading to beach on Tuesday at a certain speed. They then return to Fargo the next day, Wednesday, and drive 10 miles per hour faster. They really want to get out of beach. So the total travel time was 14 2/3 hours. And we want to find their speed on the way to beach and back. So we're going to think of it two ways, or one way. We're going to think of, because it doesn't tell us otherwise, as a straight shot, and not worry about curves or anything like that. So we know that this whole distance is 400 miles. Let's say Fargo's here and beach is here. Excuse me. And we need to know, as we're traveling to beach this way, we know we went a certain speed. So certain speed, since it's vague, excuse me. Since it's vague, we're just going to give it x as the variable. And then on the way back, we went 10 miles an hour faster, x plus 10 miles per hour. And so we need to come up with a way to solve this. Now we actually have seen this already. This is a distance problem. We have distance and we have rate, and they gave us the total time. So we have two trips. We have to beach and then to Fargo. Each one of these needs a distance equals rate times time, and a distance equals rate times time. So to beach, we know it's 400 miles, so they drove 400 miles, and this has to equal our rate, which is x, times our time. Let's call this t1. And back to Fargo, it's 400 miles again, and this is going to be x plus 10 times t2. So we have two equations, two unknowns, well, three unknowns, but we do know that T1 plus T2 has to equal 14 2/3 hours. That's the time. So we're going to solve our two distance equations that we've made here for time, because we have a relationship between them. So T1 will equal 400 over x, and T2 will equal 400 over x plus 10. So just solving these two equations for T1 and T2. And then we're going to substitute them into our start equation here. 400 over x plus 400 over x plus 10 equals 14 2/3, and 14 2/3 is 44 over 3. This is going to equal 44 over 3. And now, as I said a few minutes ago, this is back to chapter 7. We're solving rational equations. We need to get rid of the denominators. So we're going to multiply everything here by 3x times x plus 10. That's going to be the GCD of our denominators. And we distribute to each and every term. So when we multiply here, we'll have 400 times 3 times x plus 10 plus 400 times 3x equals 44 times x plus 10. Now we just simplify down. So this is going to be 1200 times x plus 10 plus 1200 x equals 44x squared plus 440x. So we have 1200x plus 12,000 plus 1200x equals 44x squared plus 440x. So collecting like terms, 2400x plus 12,000, not plus, equals 44x squared plus 440x. Now you may notice something here, and we could have done this to start, but you don't have to. Each one of these, 24, 12, 44, 440, all divisible by 4. So I'm going to make my life a little bit easier here by dividing everything by 4. So we have 600x plus 3,000 equals 11x squared plus 110x. Just to make my life a little bit simpler. Now we're going to move everything to one side, so because the x squared here, I'm going to move this stuff over. So minus 600x minus 3,000. We end up with 11x squared. 110 minus 600 is negative 490x minus 3,000 equals 0. So this definitely, it could factor, but I don't know if I want to play around with these big numbers. So we can complete the square, or we can use the quadratic formula. I'm going to opt to use the quadratic formula because I don't like completing the square that much. If you like completing the square, then go for it. So quadratic formula is negative b, or negative 490, which is positive 490, plus or minus the square root of negative 490 squared, b squared, minus 4 times 11 times negative 3,000, 4ac, all over 2 times 11. And so if we look at our discriminant here underneath the radical, we're going to have positive, negative times negative makes this positive, so we'll have 2 real solutions. And I just pop this into the calculator, because why not? we get negative 60 over 11, or x equals 50. So it just turns out this did factor. If you're curious, it was 11x plus 60 times x minus 50. Now, I wouldn't expect you to know that that factored, but we have our solutions. And so now we have to think about what is x. Well, x is speed. I don't need an arrow here. And speed, we know, can't be negative. So we're just going to cross that out. So now we take our 50, we go back to the original, way up here, and we look just like we did in chapter 7. The only things we're not allowed to plug in are 0 and negative 10. 50 is not one of those, so x is going to equal 50 miles per hour. And that means this is to Beach was 50 miles per hour, and then to Fargo was 70 miles per hour. 60. I can do math. 10 plus 50 is 60. To Fargo. Now, one thing we didn't do is check. We didn't explicitly check. We just looked at it. Is it going to cause an issue? Now, you should still check. It will work, but I'll leave that up to you. So this is the end of 11.3. So we're still using quadratic formula, completing the square, but now we're doing it for equations that are quadratic in nature, and they're not actually quadratic except for in those couple cases. Okay.